This is the assembly of a sound-damped MRI bearing by Balint, Jerica Fischer, Matthew Guy, and Alex Harpst. Our senior design project partnered with SKF and focused on investigating the feasibility of the assembly process of a pre-designed rubber liner that would induce an interference fit between an MRI bearing and its housing. MRI bearings range anywhere from 37 inches all the way up to 65 inches, meaning we first had to devise a small-scale assembly to perform our tests. We ultimately created a housing that 6-inch bearings could be pressed into, equipped with an attachment point for the material testing machine after assembly. To begin, we used FEA software to simulate the assembly process, including stresses on the housing and deformations, which could be issues later. This allowed us to develop the best assembly process to reduce interferences during assembly and ensure a consistent spring constant in the assembled bearing. We also conducted material testing to identify the best lubricant and adhesive and ensure compatibility with the rubber. These tests also helped us determine which products offered the most optimal material properties, like low friction coefficient and high bond strength. The friction testing consisted of a steel sheet to replicate the bearing housing attached to a backer for more support. The rubber was glued onto a steel block and then placed on the board, which was lifted at an angle until the rubber slid on the steel. From there, a simple calculation would tell us the friction coefficient and thus the assembly force required. This process was repeated with and without lubrication. Another test was the rubber compatibility test, which involved soaking the rubber pucks in our chosen lubricants and adhesives to make sure these assembly consumables did not vary the rubber's properties in an unpredictable way. The material property tested was compressive modulus at 10% compression. This also gave us an interference pressure for the force calculation. The lap shear test determined which adhesive was the strongest by applying the adhesive to the rubber and 2 steel plates and pulling until failure. A high failure load as well as failure in the rubber was a good indication of adhesive strength. After identifying the best lubricant and adhesive, we installed the rubber liner using the press fit method, which involved our designed small scale housing and an arbor press. Our chosen lubricant was a Dixon P80 and our chosen adhesive was a Loctite 495 adhesive. Once the small-scale bearings were assembled, we proceeded to the post-assembly testing phase. During the testing phase, we measured the spring constant of the assembled bearings to ensure that it was consistent and within required range. We aimed for a low variance in the spring constant to ensure that the bearing operates effectively and efficiently. Finally, we considered heating the outer housing of the bearing, which would make it expand and in theory could remove any interference altogether, thus negating the need for a lubricant. In the end, we decided this would be the most consistent and best method for assembling the bearings. We recommend using thermal blankets to heat the outer housing to 200 degrees Fahrenheit, at which point the bearing and adhesive bonded rubber can simply drop in without any resistance. This process addition should not incur major cost or labor additions to SKF's current system, and as the bearing housing cools down, it will simply contract and mechanically lock the bearing in place. We would like to thank SKF for supporting this project, as well as the faculty at Barron who guided us along the way.